Okay,
Only one minute.
so up until now, all of our collisions have been in one dimension. They've just, things have been going left or things have been going to the right. And now we're gonna open things up to two dimensions. And once we understand how to do collisions in two dimensions, there's no reason to go to three dimensions. That's just making things messy. Okay, so two dimensions is all that we would handle on the exam. I posted two review sessions where I've gone over those sample exams, questions from the sample exams. One was made in fall of 24 and the other one was made in spring of 24. And I'm sorry, spring of 25, so just recently. And those are at the YouTube channel that I've got up there. Because we're going over sample problems and review on Tuesday of next week, I'm not going to have a nighttime review. We'll just rely on these recordings here. To get us started, let me just have you take out your clickers and answer a few questions. Keep your clicker out. Imagine, if you will, that we're looking down on a hockey rink. And what you're seeing are two regulation hockey pucks that are coming towards each other at the same speed, one to the east and one to the north. And I say the regulation, but there's a little modification. And that is we've got Velcro around them so that when they strike each other, they stick, they stay together. So what kind of what flavor of collision is that? Shout it out. Maximally inelastic, maximally inelastic, okay? So my question to you is, after they stick, which of those directions are they going to travel together? Let me get you started here. Okay, now you can click. And yes, it's easy. If ever there was a time when we were all going to get the right answer, this would be it. Okay? This would be it. Don't make it harder than it is. Okay, is that all of us? Last call. Oh, ha ha.
That one guy.
And that's why we're not going to Disney World, people. I was ready to take you all, but that's it. Thank you. Okay. Yeah, it's gonna be C. Okay. Now let's try another one. This time, instead of two regulation hockey pucks, I've got a Mondo hockey puck, but they're going the same speed. And the question is, which of those is most likely the direction of the two after they stick, after they collide and stick?
Wait, it's on the bottom.
Okay,
So you said it.
is that all of us? Good, okay. So the answer is B. Well, no, sorry. Wrong button. So now we've got the two regulation hockey pucks, but one's going fast and one's going slow. Which of those directions is most likely to be the direction they travel after they collide and stick together? With your clicker. Okay. There we are. Okay. Great. See the answer. Let's do one more. This time I got a regulation hockey puck going fast, a Mondo one going slow. And my question is, which of those directions, B, C, or D, or can't tell, is going to be the correct final velocity. Okay. Okay, last call, get it in. Waiting for two more. Close enough. Okay, we say C. But that's not the answer. That's why we did this exercise. The answer is we can't tell. Now, those of you that said C, what you were using was a compensation argument. Well, that one's got more speed, but this one's got more mass, sixes, okay? Let me give you an example of why that's not a good way to reason. I have a grandson who's 18, a cross-country star, who is much taller than I am, but I weigh more than he does. If we take my mass in pounds, my weight in pounds, excuse me, and we multiply that by my height in inches, and we do the same thing for my grandson, are we likely to get the same number? No, no. And so that compensation argument is just not the type of reasoning that we want to use. What we want to use when we are solving these two-dimensional momentum problems, collision problems, is we need to recognize that this conservation of momentum equation is a vector equation. And a vector equation has to be true in every dimension. And so this is really two equations. I've got the X momentum that is conserved, and then I have the Y momentum that is conserved. And that's the way we solve these two-dimensional problems. Now, before we go any further, let me just make the case that this is real world stuff. Okay, this is what they do on CSI, is conserve momentum. Back in 1995, Timothy McVeigh blew up the Murrah Federal Building in Oklahoma City. 168 people were killed, including 19 children. Okay, what he did is he parked a rental van filled with explosives right next to the federal building, and then he walked away and remotely detonated it, and it just destroyed half of the building. It was the greatest, most tragic domestic terrorist attack in our country up to that date. And they didn't know who did it. But what they did know was that that truck was parked when it exploded. They knew that much. And so they knew that the initial momentum before the explosion was zero. And that means that if we find all of the pieces of the truck and figure out what the momentum of those pieces were, it should all add up to zero. Well, they went about trying to do that. They found all the pieces of the truck that they could, and judging from where they ended up, they figured out what the velocity of those pieces were, and they pieced it all back together, and it wasn't zero. They were missing something in that direction. So they went in that direction, and they found a piece of the axle that was lodged in something, and it just so happened that that axle had a identifying stamp in it that led them to Timothy McVeigh through the rental agency, and he was arrested. So this is real life, okay? When we say that energy is conserved, as I said before, that has all sorts of ambiguities there. You know, we got, oh, let's ignore air resistance, let's ignore friction, there's all these messy buckets. But there's only one bucket for momentum. It's mass times velocity. When we say that that has to be conserved, that's hard and fast. Okay, that, You can't get around it, no matter how messy the collision or explosion is. On a much more trivial scale, I got my job at Montana State University 33 years ago because the guy that had that job quit. He was making so much money working for lawyers, just going into the courtroom and telling them who was at fault in traffic accidents. And all he would do is use those equations right there and skid marks to figure out who got the ticket, who was to blame. And he just decided he couldn't afford to teach anymore, and I was thrilled to take his place. So that's how I feel about conservation of momentum. Let's look at this problem here as a first example, and I'm going to go through a lot of examples. And I've picked these examples because each one highlights a different tool that you need to have in your toolbox for that next exam, okay? So here we've got a 2,000 kilogram Volvo traveling at 15 meters per second due east, and there's a 8,000 kilogram 18-wheeler that's just lumbering along at 5 meters per second at 37 degrees north of east. And they collide and stick together such that they become one vehicle with 22 wheels and then scrape across the pavement into someone's yard. But if I want to know how fast they're going and in what direction they're going right after the collision, we don't wait until they end up in the yard. Right after the collision, how fast are they going and what direction? We would use conservation of momentum. And let me just show you how that is done. Okay, so I'm gonna draw a quick representation of the momenta. So for the car, I've got 2,000 kilograms times 15 meters per second. That's 30,000. What are the units? Franci, thank you. That makes me happy. Okay, and then for the truck, we have 8,000 times 5 or 40,000 Franci. And if this were on an exam, the first question I would ask you is, what is the total momentum of the truck Volvo system before the collision? Tell your neighbor really quick what that total momentum is. How many of you are sitting next to someone who said 70,000 Franci? Yeah, okay. Wrong or sick and wrong? Sick and wrong. Sick and wrong. Okay, sick and wrong. And the reason it's wrong is that momentum is a vector. Okay, if this were money, 30,000 and 40,000 is 70,000. That's clear. If it were energy, 30,000 joules plus 40,000 joules is 70,000 joules. But this is not 30,000 Franci. This is 30,000 Franci east. And this is not 40,000 Franci. It's 40,000 Franci at 37 degrees north of east. And so we have to treat it as vectors. Now you remember back at the first part of the class, way in the before times, right before that first midterm, I suddenly sprung on you that two-dimensional projectile motion. And some of you are thinking, Greg, why did you wait till right before the exam to spring this on us? And remember, I promised you that a two-dimensional motion problem was really just two, count them two, one-dimensional motion problems. And if you could do a one-dimensional motion problem, you can do two of them. Well, the same thing's true here. And just like with the motion problems, the most important step in the whole process is that line right there. Drawing that line right there, separating the X part of the problem from the Y part of the problem. Where I'm using the standard coordinate system where Y is in the north direction and X is in the east direction, like that. Okay? Now, if I look at the car, all of that momentum is in the positive X direction. None of it is in the Y direction. But if I look at the truck, well, I've got to break that up into its X part and its Y part. And that X part and that Y part make up a 3, 4, 5 triangle. Okay? And because this is 5 times 8,000, this is going to be 4 times 8,000 or 32,000 franci. And this is going to be 3 times 8,000 or 24,000 franci. If that 3, 4, 5 thing just doesn't speak to your soul, just go back to the trig way and say, well, this is 40,000 franci times the sine of 37 degrees. And this is going to be 40,000, that's the hypotenuse, times the cosine of 37 degrees. Okay? Now I put those in here, 32,000 for X and 24,000 for Y. And then I add up the columns to get the total momentum for the system. And this is going to give me 62,000 in the X direction and 24,000 in the Y direction. So what does that look like? Well, I've got 62,000 in the X direction. I've got 24,000 in the Y direction, and the total is the hypotenuse there. And the magnitude of that is going to be, by Pythagorean theorem, 62,000 squared plus 24,000 squared, square root. And that equals 66,500 franci. And this angle here is given by the inverse tangent of the opposite side over the adjacent side. And that gives me 21 degrees. So I would say that the total momentum of the system is equal to 66,500 franci at 21 degrees north of east. Now, is that the total momentum of this system before the collision or after the collision? Both. That's the whole point. That's the piece that stays the same. It's both. Now, here's what's confusing. After they link together, they're all moving at 21 degrees north of east, heading for that yard where they're going to end up parked. Okay? But before the collision, there's nothing that's moving 21 degrees north of east that we can see. There's an invisible thing called the center of mass that's moving 21 degrees north of east. But there's nothing that we can see that's moving that direction. But we know that the momentum, if we add it as vectors, gives us this answer, both before and after. Before and after. Now, we were asked for the velocity, not the momentum, the velocity. Now, in general, the momentum of the system is going to be the mass of the car times the final velocity of the car, plus the mass of the truck times the final velocity of the truck. But because they're stuck together, because they're moving as one unit, these are going to be the same final velocity. And so I can write that as the mass of the car plus the mass of the truck times V final. And I can just write this as the total mass of the system times V final. Now that's only going to be true if they're stuck together, if they're moving as one, okay? So now I can say this total momentum is equal to the mass total times V final, and that's what I'm looking for. So I say V final is equal to 66,500 Franci at 21 degrees north of east, divided by the total mass. I've got 2,000 plus 8,000, that's 10,000 kilograms. And that's going to give me a final velocity right after the collision of 6.65 meters per second at 21 degrees north of east. Okay? So, see if your neighbor followed that two-dimensional problem. Do a buddy check. Are there questions? Questions? Okay. Wheel on your neighbor. Who's sitting next to someone who's figured it out? No one's figured it out. No question? Okay. Let's move on. In this problem, we're told that there's a collision between two vehicles at an intersection. And vehicle A is an SUV. It has a mass of 600 kilograms, and it's going due east. Vehicle B is a sedan. It has a mass of 400 kilograms, and it's going at some speed we don't know, due north. What we do know is that when they collide, they lock bumpers and become one ugly vehicle with 8 wheels. And we see the skid marks, and we figure out how fast they were going right after they collided. And we find that it's 20 meters per second in a direction 53 degrees north of east. Now, folks, that's something you should know how to do. For example, we found here how fast this truck Volvo system was going right after the collision and what direction. But I could also ask you another question, and that is, how far do they slide before they stop? How many seconds do they slide? If I ask you how far they slide, what are you going to use to solve that? Energy or momentum? Got it out? Energy. What if I ask how many seconds do they slide? That's momentum. Okay, that's momentum. Okay. So, in this problem, you are the investigator, and you're asked to come and testify who should get the ticket. And in this neighborhood, the speed limit is 30, by which we mean 30 meters per second, 60 miles an hour. They don't really love their children very much in that neighborhood. Okay, and you're laughing, but between our house in Bozeman and Helena, Montana, where we would go to the new temple, my wife and I were called as temple workers, and we drove that road a lot. And when you were about 20 minutes outside of Helena, there was a little white schoolhouse right next to the freeway, right next to the road. They don't have freeways out there, just 2-lane roads. But they had a sign right there saying it's a school zone, speed limit 55. I mean, you got to slow down for those school kids that are crossing the road. They were quick kids. Okay. So in this problem, we want to know who's going to get the speeding ticket. And so tell your neighbor how you're going to go about solving this problem.
Starting up. It's gonna do it.
Okay, I want to emphasize that the most important step in solving one of these two-dimensional problems really is that line separating the X part from the Y part. And here we've got car A, car B, and the total. Now, I suspect that on that second midterm, some of us saved some of our scratch paper by not drawing free body diagrams. How did that work out for you? Yeah, not so good. Okay, on this next exam, it's been my experience that some of you will try to save scratch paper by not making the table. Now, we give multiple choice tests here because there's so many of you. But for 31 years, I was given long answer tests that I would grade until 2 in the morning. And I went through lots and lots of exams. And what I saw was that the people who saved themselves some time by not making the table also didn't get the right answer. Okay, so I would suggest that this is what you want to do. For A, all of the momentum is going to be in the positive X direction, 600 kilograms times the A, and none of it in the Y direction. For B, all of it is in the Y direction, and it's 400 kilograms times VB. Now, because the total momentum is conserved, it's the same before the collision or after the collision. I know what it is after the collision, so that's what I'm going to use. I've got this momentum total. That's going to be a total of 1,000 kilograms times 20 meters per second. That's 20,000 Franci in a direction that's 53 degrees north of east. Now, again, this is going to be a 3, 4, 5 triangle. And since this is 5 times 4,000, this is going to be 3 times 4,000 or 12,000. And this is going to be 4 times 4,000 or 16,000 Franci. So I come in here and I put that in my my X and Y column. This is 12,000 Franci, and this is 16,000 Franci. And now I just add up my columns. In the X column, I have 600 kilograms times VA plus 0 is equal to 12,000 Franci. That gives me a VA is 20 meters per second. They do not get a ticket. Well, when I add up the Y column, I get 400 kilograms times VB is equal to 16,000 Franci. And that gives me a VB is equal to 40 meters per second over 80 miles an hour. They need to be thrown in jail. They need to be thrown in jail. Okay? Check that your neighbor's on the bus with that.
Simpler than I thought.
It cannot. That's what conservation means. It cannot change. If it were to change, you would violate Newton's third law and the universe would crash in on itself. No, it's conserved as a vector. The X part is conserved and the Y part is conserved. Brinley, you had a question?
Yes, what I was like, says.
Says, if you check, see if this is finals.
I need a break.
87. Right after my next. It's on
Sine of 53 is equal to, it's equal to the opposite over the adjacent, which is the Y part.
Use out.
Why belong?
Right.
30.
I know what you mean.
I'm not sure I understand your question.
It's like.
Like,
Oh,
oh, because it doesn't. Mass, never mind.
Yeah, it's mass times velocity.
And he was like, I'm so good.
What did you get? 20,000 Franci?
Oh, the 20,000 Franci,
You guys just said study.
momentum is mass times velocity. And so the mass, when they were together, was 1,000 kilograms times the velocity was 20 meters per second at 53 degrees north of east. When I multiply this together, I get my 20,000.
Like a year.
Okay. Now, questions on this before we go on to the next one?
She's on the sidewalk.
This one's right out of your homework. You've got,
What record was supposed to happen?
you've got 3 children that are stuck on a frictionless pond of ice. I don't know how they got there. I don't ask questions. Okay, but they try to get off, they try to scoot their feet and they go nowhere. And so they're standing there puzzling, how do we fix this? And so what they do is they all lock hands and they say 1, 2, 3, push. And they essentially create an explosion that pushes them away from each other towards the edge of the pond. Now, the first question in your homework is compare the impulse on child 1 to the impulse on child 2. Now, folks, again, this is an old exam question. Most of the homework problems are old exam questions. And when this was on an exam, I had a whole big chunk of my class that said, ho, ho, Greg, you can't fool us. You taught us that in an explosion or a collision, the impulse is 0. So it's 0 for child 1, 0 for child 2, same, ha, ha, that was easy. And that's what they got was 0 points. 0 points. The impulse on the system of all 3 children is 0. And that's why the momentum of the system of all 3 of the children is conserved. But if I just look at child 1, the impulse on child 1's not 0. Okay, if I, let's find out what it is. If I use the general momentum equation for child one, I get the initial momentum for child one plus the impulse on child one is equal to the final momentum of child one. She starts out just standing there with zero momentum. And then we add that impulse from the other two students, the other two children. And what we get is her 50 kilogram mass times her 4 meters per second north. And that gives me 200 Franci north. That's not zero. If I do it for child two, I've got zero momentum to start with, and then I add the impulse on child two, and then her final momentum is the 30 kilogram mass times 5 meters per second east. And that's going to give me 150 Franci east for the impulse. And so clearly in this problem on your homework, you were asked to compare the magnitude of the impulse on child one to the magnitude of the impulse on child two. And clearly 200 is bigger than 100. So it's bigger on child two. I did not say that. It's bigger on child one. If you say that I said that, I'll call you all liars, okay? Who are they going to believe, me or all of you? Okay. The second part of this homework is to find the final velocity of child three. And again, when this was on an exam, we had a big chunk of the students that said, well, child one goes this way with 4 meters per second. Child two goes this way with 5 meters per second. And so that means child three has to cancel out this 5 and also has to cancel out this 4. And so that's going to give me a final velocity for child three of square root of 4 squared plus 5 squared square root. Wrong or sick and wrong? Sick and wrong. That just makes me sick and tired. Why is it sick and wrong? Because there's no conservation of velocity. There's only conservation of momentum. And so we have to go back to our table. And I don't have to erase all of the table. But I know that 1, 2, and 3, I know that for child one, the final velocity is all in the positive y direction. And it's going to be 200 Franci. I know for child two, the final velocity is all in the positive x direction, and it's 150 Franci. And what I know is that the final velocity, the final momentum has to be the same as the initial momentum. They started out just huddled together, standing, looking at each other, asking, what are we going to do? So they started with zero momentum. And this column has to add up to 0 here, and it has to add up to 0 there. That means that this x part's going to be a negative 150 Franci, and the y part's going to be a negative 200 Franci. Okay, so if we go back and we use momentum instead of velocity, they start out with 0 momentum, and afterwards we've got 200 Franci this way. We've got 150 Franci that way. And it's got to add up to 0, so that means that the X part has to be a negative 150 or 150 in the negative X direction. And the Y part has to be in the negative Y direction, 200 Franci. Well, the total momentum, this is a 3, 4, 5 triangle. So this is going to be 53 degrees. This is going to be 250 Franci. Does everyone see how I got that? Yes.
How do you know if it's 53 or 37 again?
How did I know it was 53 instead of 37? Because the 37 degrees is always across from the smaller side, and the 53 is always across from the bigger side. If you think of a 45-degree angle, the sides are going to be the same, and 53 is bigger than 45, 37 smaller than 45. Okay? Now, we weren't asked for the final momentum of child 3. We were asked for the final velocity of child 3.
Yep.
But if I use the fact that, let me write it right here. The final momentum of child 3 is just the mass of child 3 times the velocity final of child 3. Then I can write the final velocity of child 3 is going to be 250 Franci at 53 degrees south of west divided by 50 kilograms. And that's going to give me 5 meters per second at, oops, didn't spell that right, at 53 degrees south of west. Check on your neighbor, do a buddy check real quick. See if they're still hanging in there.
Understand.
Because it's rating momentum.
Okay,
250 is the one.
So there's momentum for child one.
He's doing it. It'll get you the same.
any questions?
Your child has to cancel. The initial momentum is 0. Nothing's happening. Times 0. And then after time 0.
So my question is why did
Because after conservation of momentum. So if it starts at 0 momentum, then it has to finish at 0.
But you did. Sorry, Yama.
Yeah.
Okay,
Sideline.
yes.
What?
Is your question or Rebecca?
Mine.
So.
They were just standing there to start with, before the collision. Yes, always with the system. And if they're all three just standing there, there's no momentum. The velocity is 0 for all three. Okay, if you take that exam preparation sheet and turn it over, you get this problem with the asteroid.
I didn't think you were gonna go.
And you'll notice on one of the sample exams, there's a problem similar to this where Superman breaks up an asteroid that's heading for Earth. And folks, I have a feeling that you're going to have a problem that's in ways similar to this one. I'm clairvoyant that way. Okay, so this would be a good one to know. This one asteroid is heading in the horizontal direction out in space at 3 meters per second, mass of 250 kilograms, and it explodes into 3 fragments. And we are told that the velocity of this fragment, fragment 2, is 5 meters per second, but we're not told the velocities of the other two. But we are told the directions that they all go. This one goes back, and this one goes 53 degrees above horizontal. This one goes 37 degrees below horizontal. And we are asked some questions there. Who is missing this handout? Raise your hand. Okay. Would you do that for me? Okay. Raise your hand and he'll bring you a handout there. You notice I'm not erasing the table, just the contents. Okay.
Needs more.
So, anyone over here need the handout? Thank you so much. The first question on there asks us to find the X and Y components of the asteroid's momentum before the explosion. Well, it's all in the X direction. None of it is in the Y direction. And that P total is just the mass of 250 kilograms times the speed of 3 meters per second, and it's in the positive X direction. Okay? And that's going to give me 750 Franci in the positive X direction. Now, after they explode, this will be after the explosion. It's still got to be the same for the total. So if it was 750 Franci in what we're calling the X direction before, it still has to be 750 Franci in the X direction and nothing in the Y direction. Now, part B is completely out there. It's just what's the kinetic energy of the asteroid before the collision? And that's just a, do you remember the formula? And that's going to be 1/2 times 250 kilograms times 3 meters per second squared. Folks, again, I'm an old man and I see over and over again people losing points because they don't square that. Okay? Turn to your neighbor and say, that'll be you, not me. Okay.
Oh, it's not me.
Okay. Well, now let's go back to the real part of the problem. And that is part C, the X and Y components of fragment 2 momentum after the collision. Well, I know that its velocity is 5 meters per second and its mass is 120 kilograms. And that's going to give me a momentum of 600 Franci at 53 degrees above the horizontal. And if I break that up into an X part and a Y part, again, this is going to be 3, 4, 5 triangle. This is going to be 3 times 120 or 360. This is going to be 4 times 120 or 480 Franci. Another way to do this might be easier for some, is to just take the velocity of 5 meters per second and break that up into its parts. This would be 3 meters per second and then 4 meters per second. It's clear that's a 3, 4, 5 triangle, right? And then to find the momentum, I just take the mass times 3 and I take the mass times 4 to get these guys here. That makes sense? So I can come and put that into my table. For 2, I've got 360 and 480. Now, the next part asks us to find the X and Y components of 3. But they don't tell us how fast 3 is going. So that seems like we're not given enough information. But of course we are, because we know that fragment 1 has 0 momentum in the Y direction. And we know that this Y column has to add up to 0. And so that means that the Y part of fragment 3 has a momentum of negative 480 Franci. That's the way that column's going to add up to 0. So if I look at fragment number 3, I have an X part and I have a Y part. The Y part is 480. And I know that the total momentum, it's traveling at 37 degrees below the horizontal. So that would be P3 after the collision, after the explosion. If I know this is 37 degrees and I know the opposite side, what trig function is going to help me find the adjacent side? Tell your neighbor, what trig function compares the opposite side and the adjacent side? Sakatoa, Sakatoa, Sakatoa.
So 8.
Okay, I hope that you said tangent. The tangent of 37 degrees is going to equal the opposite side, which is 480, over the adjacent side, which is the X part of 3. And the tangent of 37 is going to be on the front page of your exam. That's 0.75. And that's going to equal 480 over px3. And so now I can just cross multiply to get px3. That's just going to be 480 Franci divided by 0.75, which is 640 Franci. Okay. So I come over here and put 640 Franci. Now we want to know how fast is fragment 1 traveling. So what we know is that the momentum of fragment 1 is 50 kilograms times its velocity. Well, in this case, I know that it's going in the negative X direction. So what I'm going to do is put a minus sign here and a VA. And by putting that minus sign there, I've already taken care of the direction. So VA is just the speed. Okay, I should expect a positive number for VA when I solve for VA. Okay, because I've already taken into account the direction with that minus sign. Does that make sense? Okay, so now if I add up this column, I better get 750 Franci. So let me do that. I've got negative 50 kilograms times VA, the speed, 360 and 640. When I add those together, I get 1,000. And that's got to add up to 750 Franci. Well, if I subtract 1,000 from both sides, what I get is negative 50 kilograms times VA is equal to minus 250 Franci. And that gives me VA is equal to minus 250 Franci over minus 50 kilograms. And that gives me 5 meters per second. So fragment A is traveling at 5 meters per second after that explosion. How we doing? Okay, questions on that? Now, the other way you could do that is instead of making VA the speed, you could make it the velocity, and you could just make that 50 kilograms times VA. In which case, this would be 50 kilograms times VA, and you would end up with a negative 5 meters per second for the velocity. Either way, because we asked for the speed in that homework problem or that exam problem, I put the minus sign out front so that the answer for VA would be the speed. Okay. Reese, you look concerned.
Got it.
Got it?
Yeah.
Okay.
It was
Okay.
just that I would, when it was a positive number, I was adding all that up and it was becoming more than 750 and I thought that's gotta be negative. Okay, okay.
Other questions? Okay. Now, on the exam, there's one concept we haven't covered yet. And it's going to be on the exam, but just in a very simple way with just a couple of very minor questions. And I just want to introduce that idea. We'll talk a little bit more about it on Tuesday. And then on Tuesday, I'm just going to work sample problem, sample problem, sample problem, trying to get you ready for the exam. It's the idea of power. Power is the only thing we haven't covered yet. And let me just introduce it this way. If I tell you that Greg can do 5 billion joules of Werk, and I ask you, is Greg a powerful man? What question do you want to ask me? Brave soul? Yes.
How long does it take?
How long does it take? Okay. Can Greg do all of that Werk in a minute, or is it going to take the rest of his life, 3 years? Okay. So old people, they make those jokes. Then they eat green jello. Okay. So how much time does it take to do that Werk? And that's the idea of power, is how quickly can we do the Werk? The power is how much Werk Greg can do in 1 unit of time. That unit we typically take as 1 second. And so the definition of power is just the Werk divided by the time. And folks, this is something for your toolbox. This is general. If you have a definition that is a ratio, something divided by something else, the way you get a gut feeling for what that means is by setting the basement equal to 1, in this case, 1 second. And then power is equal to that Werk that can happen in 1 second. That's the gut level understanding, okay? Now, because Werk is what changes energy, you can also write it as the change in energy that happens in 1 second. Now, there's a special case where you're pushing something across a table at constant velocity. there's obviously friction there because if you were pushing on a frictionless table, it'd be speeding up. But if you're pushing on a table with friction such that it's moving at constant velocity, we can write it this way. Verk is just force times the displacement, delta x. And if we write that delta x over the delta t, we can write that as the force times the velocity. But this formula is only valid if the force is constant in time and the velocity is constant in time. So just that special case, which happens quite often, of something that's being pushed at a constant velocity, fighting friction. So the power delivered by the hand, if the hand is always pushing 50 newtons, 50 newtons, 50 newtons, 50 newtons, and the hand is moving it at 4 meters per second, is 200. What are the units of power? Watts? Oh, no. I should have thought of that. No, it's watts. What? Watts. Okay, watt. This is as far as the morning class got. And so we'll pick this up when we come together on Tuesday. Now, folks, I beg you, I moved the due date for tutorial 8 back to Tuesday because Dr. Benyon moved it back for his class, and I figured it would only be fair if we had the same due date. But I definitely think that you should do that homework before you go to take that exam. Okay, I would encourage you to do that homework before you take that exam. Have a great weekend, folks.
Guys.
I can do it.
I saw that, like.
You're not gone at all?